Okay, so at this point in time, we have essentially shown you the four different types of arrow pushing steps that we're going to utilize quite extensively overall in this course, right? And so what we'll find is that the majority of the mechanisms that we're going to use to explain various reactions are just some sort of combination of these four basic steps. And that's not always going to be true. Like, we will get into later information where we do have to introduce other steps, but the majority of reactions kind of just revolve around these four different steps, right? So we had nucleophilic attack, we had loss of leaving group, we had proton transfer, and then we had carbocation rearrangement, okay? And so sometimes you'll be asked to either, let's say, identify the various steps that are involved in a mechanism, or you'll actually be asked to utilize them to show what the overall mechanism is for a reaction, right? So for example, let's say we had a problem here where they want us to identify each arrow pushing pattern for the following mechanism, right? And again, a mechanism in organic chemistry is like our proposal of this series of these four steps for taking our initial reactant, so we'll have initial reactant over here, and making our overall product over here, okay? All right, so let's say we start out here with our reactant, right? And note that every time we have an arrow, we essentially have a step, right? So if we look at this guy, we've got an oxygen, right? We have an arrow coming from the lone pair of electrons on an oxygen, and it's going out and attacking HBr. Specifically, it's going out and taking an H from HBr. So hopefully you guys should recognize that this is what we would call number one, or this is what we would call proton transfer, right? We have a base, right? We have a lone pair of electrons. That base is going out. It's forming a bond with a proton with hydrogen, right? And the electrons that are in this hydrogen whatever, or hydrogen bromine bond, are being left behind on the bromine, the conjugate base, right? So this is a base. It's going and getting a proton from an acid. This is a very canonical proton transfer step, which we just went over, right? So you should be able to see that this guy, in going from reactants to products, gains a proton, and those arrows are very specific with the proton transfer. All right, so then if we move on, so that was, let's say, step one of our mechanism, proton transfer. We are left with a nice little intermediate here that actually has an extra H on the oxygen, right, from that proton transfer step. It also has a positive formal charge on the oxygen, right? And so if we look at the arrows that are occurring in this step, we have electrons that are in this bond specifically that are just going off, and they're going with the oxygen. The bond is breaking, and essentially what we're losing over here is water specifically, right? And so we usually abbreviate that, this minus H2O over the arrow. So if water just leaves or something just leaves, what type of step is that, right? Of the four that we just learned, right? We had learned nucleophilic attack, proton transfer, loss of leaving group, carbocation rearrangement. So hopefully you guys are able to see that just something taking electrons, breaking a bond, is specific for loss of leaving group. And this step, which is, again, what we're doing right here, we're identifying each step, is our nice little loss of leaving group pattern overall. Okay, so if this guy just leaves, which is what just happened, right? These electrons go with the water, we lose water in this process, then this carbon is going to be deficient in the number of electrons, right? So in this process overall, what we're doing is forming a carbocation, okay? So we have a carbocation, and now, again, they've already given us the errors. They're telling us what's happening. We have something, hopefully you guys can see, shifting over, right? And so if we look at this, we know we have a carbocation. Something is shifting over to fill that carbocation positive charge. What type of our four basic steps is this, right? Is it proton transfer? Is it loss of leaving group? Is it nucleophilic attack? Or is it carbocation rearrangement, right? So the answer is carbocation rearrangement. Right? And again, all I see is a carbocation, and I see carbocation. I see specifically, this is not a hydride shift, but this is specifically a methyl shift. I see a methyl group shifting over to fill that positive charge. So we had 1 proton transfer, we had 2 loss of leaving group. Our third step in this mechanism is a carbocation rearrangement. Again, we're taking our carbocation from carbon 2. That methyl group is now forming a bond at carbon 2, and we have shifted that carbocation to carbon 3. Okay? All right, so then we get down to our fourth step in the overall mechanism, right? We have a positive charge, right? We have a carbocation. Carbocations, while they're susceptible to rearrangement, are also very good electrophiles, right? And so we have an electrophile here. And then we have this nice, very electron-rich species just coming along, right? This nice bromine from our conjugate base up here, right? And if we're looking at this, we have bromine, it's electron-rich. It's appearing, at least, to go in and attack our nice electrophile, right? So specifically, we had 4 steps: proton transfer, loss of leaving group, carbocation rearrangement. This fourth step is instead going to be the one that we initially introduced, which is our nucleophilic attack, right? So we have nucleophilic attack. Again, we have an electrophile, our carbocation, being attacked by our nice little electron-rich species, which again is called a nucleophile. A bond is forming between our nucleophile and that positive charged carbon on our electrophile, and we get our overall long-term product, okay? So these are, again, we're going to be utilizing these arrows. And the whole purpose of this is to get comfortable with using these arrows. Number one, and I think I talk about this in a second, if we're drawing arrows, we have to be very deliberate in how we're drawing them, right? Exactly where electrons are coming from, where we're putting the tail of our arrow, where they're going to, where we're putting our head. And then a lot of it is just kind of being able to identify. Like if I do give you arrows, I need you to be able to identify which of these 4 basic steps are being utilized, okay? Now, again, a mechanism is kind of like a roadmap, how we think this reaction occurs, okay? And in this mechanism, in going from our initial reactant to our final product, we have proposed that this mechanism or this roadmap occurs in 4 separate steps, right? We propose that first off, we see a proton transfer step. Second, we'll see loss of leaving group. Third, we see a carbocation rearrangement. And fourth, we see a nucleophilic attack, right? Again, we're trying to explain how this guy gets to this guy, okay? Now, in this last little bit, I wanted to mention briefly, or go back briefly, to our transition state or our energy coordinate diagrams that we talked about at the very beginning, right? Where we have energy here, and we have, what is this at the bottom? Some weird reaction progress. Let me spell that a little bit better. Reaction progress, or reaction coordinate. Right? And again, we have our reactant going to product. Let's say we know that this is a nice exothermic reaction. And say we have our reactant, we have our product over here. So they're different. We have product at a lower energy state than reactants. The question is, what does it look like in the middle? Right? If we have proposed this is our mechanism, how many different humps do we think there are in between the R and the P, the reactant and the product? Right? And so the answer to that is however many steps that you guys have proposed for your mechanism is how many different humps are going to actually be in the overall reaction coordinate diagram, right? We have 4 separate steps here. And so each step is going to have its own little activation energy. It's going to have its own little rate law, right? And so in going from R to P, we would draw that in 4 separate humps. And of course, I've not planned that super well, so 4 separate humps, okay? So we have 4 separate transition states, 4 separate humps. Relatively right now, like who's the largest, we're not going to take any meaning from that. We're going to talk about in a second which step we could potentially anticipate to be the rate determining step or have the largest activation energy in the overall diagram. So don't take any meaning at all from how large I've drawn these But just note that depending on the number of steps depends on the number of overall humps in the diagram, right? If we have 4 steps, there are 4 separate humps, 4 separate activation energies, etc. And just as a note too, each of these guys in the middle, right? These things that we have drawn, these things that we have drawn, these things that we have drawn, these would be the various intermediates in our separate steps, okay? They're not the transition state. The transition state is short-lived. You're never going to see it. These guys instead are proposed intermediates in the overall mechanism. And again, intermediates are these nice little local minima in between our separate steps. Okay, so go ahead and again, trying to utilize what we have just learned with respect to these arrow pushing patterns and predicting various mechanisms. I want you to do this problem, right? So in this, I've given you a mechanism, right? And specifically in this mechanism, we have 2 potential steps. Again, we have our reactant over here. So we've got our reactant going to form our products over here. And I've given you the arrows for these, so I'm wanting you to identify which steps are being utilized in this mechanism. So specifically, what step is this guy? And then second, what step is this guy? So again, go ahead and pause the video, give this a shot, try to identify the steps, and then come back for the answer. Okay, so in identifying this, the first thing I'm going to look at is where essentially my arrows are starting at. All right, so I have 2 arrows in this step. I have an arrow that starts at this OH, this hydroxide molecule. All right, so we've got an arrow that starts out here. It's going and attacking, or it's doing something to this carbon, right? We're forming a bond between that oxygen and this carbon. But as is right now, if we were forming, let's say, a bond here and nothing else occurred, right, with respect to this carbon, we would have 1, 2, 3, 4, 5 bonds to carbon, which is not possible, right? So in this process of this oxygen forming a bond with carbon, we're also losing the pi bond between the oxygen and the carbon up here. Okay, so we have a nice electron-rich species. It's donating an electron to this, or electrons, pardon me. And hold on, I don't like that arrow at all. It's going and forming a bond between it and this carbon, right? And in the process, the electrons of this pi bond are going and essentially going to this oxygen, right? And so now we've got oxygen up here with 3 lone pairs of electrons and a negative formal charge. We have our carbon with its bond to this oxygen, okay? So hopefully this guy's nice and electron rich. This carbon specifically is electron poor, right? And this is due to electronegativities. It has a double bond between it and oxygen, which makes it nice and partially positive charge. We have our partial negative up here. So we have electron-rich species with this hydroxide. We would call that a nucleophile. We have our electron-poor species up here with this carbon. We would call this an electrophile. And we have a nucleophile attacking an electrophile. So hopefully you guys recognize that this was nucleophilic attack. And again, with nucleophilic attack, it can occur in 1 step, right, which is what we saw in that previous problem, or it can occur in 2 if, again, we have an issue with obeying the octet rule, right? If we're going to form a bond here, we can't have carbon with 5 bonds, so the electrons of this pi bond are going to have to move. We're going to have to break that pi bond. Okay, so that's number 1, nucleophilic attack. Number 2, we come over to our nice little intermediate here, and what we find is we have electrons moving from this oxygen, right? They're going to form a double bond, or a pi bond again. And again, let me try to specify that a little bit better. We have these guys going to form a double bond between this oxygen and this carbon. Again, we can't have that happen, right? Because Carbon, again, can't have more than 4 bonds, right? And so as a process, we're actually going to leave, or we're going to lose this guy, right? So the bond between this carbon and this oxygen is actually breaking. Those electrons are going with this methoxide group, or this, it's methoxide. I'll just say methoxide. Okay, so again, we had nucleophilic attack that gave us our intermediate. In the second process, we have electrons coming down, and essentially they're pushing out this methoxide group, right? So it's not proton transfer. There's no transfer of protons. There's no rearrangement of a carbocation. We've already seen nucleophilic attack, right? So for this guy, what we see here is loss of leaving group, and I'm going to abbreviate that LG. And again, it's one of those situations where usually loss of leaving group occurs in just one arrow, but for this one, loss of leaving group occurred in 2 different arrows. We had an arrow here, we had an arrow here, and that was due to the fact that, again, we have to obey the octet rule. So this guy, at the end of the day, is our leaving group, and then this is our main neutral final product. So we had 2 different steps here. We had nucleophilic attack originally, so nucleophilic attack, and then second step we had loss of leaving group. Again, usually I will ask you to draw the reaction coordinate diagram. If you're going to do that here, mainly what I want to see is the fact that there are 2 humps to this reaction, right? So we have reaction progress. We have our reactant starting up here, and in this 1-2 steps, we've gone from reactant to product down here. Okay, so again, we're drawing the arrows for these various patterns, okay? Now, how do I know what's going to happen in this reaction? Who should I go to for inspiration and knowing exactly what's going to happen?
Products.
The products, right? So in the products, what have we done? We've broken this double bond, and what have we formed in the process?
A single bond and
right, we formed a single bond with an OH specifically. And so again, who is the other reagent here? OH, right? So we know probably what's going to happen in this overall first step. We're going to have our OH do what? Attack this carbon, right? So we're going to see nucleophilic attack. I'm going to specifically draw the arrows starting at the electrons and going directly to the carbon that it's attacking, okay? So that's number 1, nucleophilic attack. What else needs to happen here, though?
the double bond needs to move.
Right, so I'm going to have to use a second arrow to break that pi bond and put those electrons up on that oxygen. Because if I don't, I'm going to end up with 5 bonds of carbon, which is bad. This is a bad example. It's stupid. Okay, so first step, nucleophilic attack, right? Now I have this, my nice little reaction intermediate. Again, who am I going to go to for inspiration on what happens in this next step?
The charge.
Got this guy. To know exactly what happens now, I've got to go to see what it forms, right? And going from here to here, what has happened comparatively? We have reformed this double bond, and who have we spit out? This guy, right? So this guy's ethoxide comparatively to methoxide. But again, this guy versus this guy, we've reformed the double bond, and we've spit out this part of the molecule. Okay? So in this next step, what is this? This is another version of loss of leaving group. We're going to see the electrons in this pi bond come down, or in this lone pair, pardon me, come down, form our pi bond. In the process, these electrons are going to go with our leaving group, with the oxygen. So 2 separate arrows, again, representing 1 overall step, loss of leaving group. Okay, so finally, we have one last step, right? We have this guy, which we're happy with. We've got this guy, and looking at this versus this, what have they done, respectively, between the two?
Acid.
Transfer.
They just transferred this guy. We transferred a proton. So this last step is what? Proton transfer. So this last step, number 3, is proton transfer. How do I draw a proton transfer? Where do I start my arrow?
The hydrogen.
Whoever's gonna grab it.
Electrons. We always going to start at electrons, right? Who is the acid and who is the base here? This guy is the proton donor or proton acceptor?
That one's the acid.
This guy's the acid,
Right.
right? It's donating the proton. This guy's the base. It's accepting the proton. We're always going to start the arrow at the electrons of the base going to get that proton, right? So arrow starts here, goes and takes that proton. I can't have more than 2 bonds to hydrogen, so what has to happen to these electrons in this bond?
That one's gonna break up.
They're going to stay behind on our new conjugate base. So proton transfer always involves 2 arrows. We have base going to take the proton, the electrons in that bond staying behind on whatever they're coming from, on the new conjugate base. Yes?
Why'd you make the... Oh, wait. So, make the lone pair go to the hydrogen because it's kind of swapping out? Is that why? Okay.
So the base, again, in this proton transfer step, this guy at the end of the day is going to have that proton. It's going to have a bond with that proton. These electrons are what are forming that bond. It's the electrons on the base that are forming the bond between the 2 of these. Again, because hydrogen can't have more than 2 bonds, it has to break this as opposed to...
Ooh, okay.
So anytime we have electrons starting somewhere and going somewhere, we're forming a bond directly between those 2 things.
All right.
Okay, so nucleophilic attack, loss of leaving group, proton transfer. Again, when I'm asking these types of questions on the quiz, on the exam, your arrows need to be specific. They can't just be, oh, it kind of starts over here and it goes to wherever. You need to specifically point to where you're going and then what's being left behind, etc. Okay?
And make sure both arrows have the exact, like there's no 2 steps. Because that's what confused me here. If I just left the loss of group and then the cation.
So you wanted to form a carbocation there. For
See
this
what I'm saying
one,
now?
yeah, I see what you're saying. For this one, it was specific. Like there can be other situations where we do just see the leaving group leave and it doesn't need the second arrow. But for this problem, because the arrows were drawn, yeah, they represent the same.
Okay.
But yeah, we will see loss of leaving group where something just leaves and there's not a second arrow that goes with it.
So just look at my product and that's what gives me what
Yeah,
step it is.
what step it is.
Thank you.
Okay, so then finally, we do an example. What follows next usually, I have you guys do. Okay, so finally, I want you guys to attempt one of these on your own, or I guess 2 of these. They're 2 separate steps. So here I give you your reactants, I give you your products, I give you your intermediates, and I want you to draw the arrow pushing that would accomplish each of these steps, right? So this reaction is sequential, right? I think I ran out of space when I was writing this, so like this guy down over here is the same as this. It's like a 1 and then a 2, but it doesn't really matter. You can look at this however you want. I'm looking for the arrows that are required for both of these steps. So go ahead, give this a try, and then come back for the answer. Wait, oh, sorry, I forgot. Okay, so if we start here, let's say that we start at step 1. We'll note that in going from this guy to this guy, right, we formed a bond. right? Specifically, we formed a bond between carbon and oxygen, right? So again, we have a nice positive charge here on our carbon. We've got oxygen here with 2 lone pairs of electrons. Ideally, you should be able to say, oh, well, oxygen and water, that's kind of a weak nucleophile. You won't need to know that it's weak until next chapter. This is a nice electrophile. So in going from here to here, we're likely going to see nucleophilic attack, right? So with nucleophilic attack, we've got the arrow starting on the electrons of the nucleophile, and they're going towards, the head is going towards whatever this electron deficient center is on the electrophile. All right, so we're going to have our arrow starting here and going to form a bond with this carbon. And again, I'm very specific about where my arrow starts and where my arrow ends. So this is just one arrow is needed for this because, again, we're going to a carbon that already has a deficiency of electrons, so we don't have to worry about the octet rule. And the product overall is this nice little intermediate over here. Okay, so again, we're going to go ahead and skip down to this guy because it's the same exact thing. This essentially just becomes this. Ignore that as an arrow. That's not an arrow. Yeah, okay. So now we're here, and we want to get to here. This is how we're actually going to do this, okay? So note that the only difference between this species and this species is what happens at this oxygen, right? For this oxygen over here, we've got a positive formal charge. It has 3 bonds and 1 lone pair of electrons. And over here, we have a neutral formal charge. We've got 2 bonds and 2 lone pairs, right? We also have a hydronium ion over here, whereas we had just a water over here, right? So the only thing that's different between our reactants and our products here is the movement of a proton, right? It's the movement of an actual hydrogen. So hopefully you guys should be able to identify that while this guy, number 1, was nucleophilic attack, our second step is not nucleophilic attack. There's no carbocation rearrangement. There's no loss of leaving group. Instead, what we're seeing here in our second step is a proton transfer step. Right? And so in a proton transfer, we have our base. Our base, again, is going to have our electrons that are going to form the bond. This guy is our base. It's got a nice lone pair of electrons. It's going to go out. The base is going to go out. It's going to take a hydrogen from the acid. Right? This is our acid. The electrons that are here are going to stay behind. Right? And as a result, we get our hydronium ion, our H3O, and we get our neutral product overall. So in proton transfer, unless we're abbreviating it with the H's, then it's usually almost always going to have 2 separate arrows. Again, the base going and getting the proton, and the electron staying behind on the conjugate base. Okay, so that's it. You guys should be fairly proficient in your arrow pushing, drawing arrows, being able to identify the 4 separate patterns that we taught you. And again, then being able to identify what the reaction coordinate diagram would look like, ideally, given whatever mechanism that we're proposing.